Hello. A new background today. Okay, just wait for a few more minutes. All right, no one's here. Oh, it's not recording, so might as well go through some of the problems. Do you have any questions you'd like to go through? Any particular ones? Ah, okay. Hello, people who have joined. Otherwise, okay, we'll start. We're talking about sets. We continue talking about sets today, and we're going to go into a bizarre world. Like, well, we did last week. It was a bizarre world where you could have hotels, infinite rooms, and infinite hotels. We're going to carry on. So we have a Christmas party, and we have two Santa Claus, two Santas. You should be able to see the screen. We have a kind. So sorry for this, for the ill-written problem. It was that's not the point. Don't focus on the problem. So I'll describe it. We have two Santas. We have an evil Santa and we have a good Santa. And Santa number one, which we don't know who's evil or not, he's giving out candy to children. So Santa one. So what he does, he gives out 10 candy 1 minute before midnight. So he's giving out candy at 1 minute before midnight on the Christmas Eve. 1 minute before midnight. First time. So that's n equals 1. Then half a minute before midnight, he gives out That's the second time he gives out candy. And then a quarter of a minute, etc. Quarter, 1/8 of a minute. Basically, it's a finite time, right? So he's only giving out candy to children in the 1 minute before midnight. First, exactly 1 minute, then 30 seconds before, then 15 seconds before, then 7.5 seconds before, etc. Now, Santa number 1 in room 1, so room 1, Santa 1, he's giving out 10 candy, and each candy has a number on it. 1, 2, 3, 4, 5, 6, 7, 8. That's 9, 10. So Santa number 1, so 1 minute before midnight, he's giving out candy number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. He immediately takes back candy number 1. So he takes a candy from children. He takes candy number 1. Half a minute before midnight, he gives out candy number 11, 12, etc., up to 20. And he takes away candy number 2. A quarter of a minute before midnight, he gives out candy 21, 22, etc., up to 30, and he takes away candy number 3. Okay, yeah, does that make sense? It's a weird, bizarro Santa. He gives out candy but takes away just 1. He gives out 9 candy and gives away 10. So how many candy do we have after n steps? N steps. Well, after n steps, he has taken n candy. He has given 10 n candy, right? That makes sense because every time he gives out candy in tens, and he has taken candies 1 through to n. Right? After 3 steps, he has taken 3 candy, the first 3 candy. So after we have after n steps, the remaining candy is n plus 1, n plus 2, etc., all the way to 10n. Right? Because we've taken the first n candy. So the first candy that we have untaken is n plus 1. And in total, we have how many candy? Somebody tell me, how many candy do we have in total after n steps? 9n. Very good. Thank you. Thank you for paying attention. Is everyone clear with this? Do I need to explain something? Do I need to explain more? It's clear. Good. Santa number 2 does it differently. Santa number 2 Santa 2. So he gives out candy candy from 1 to 9. So 1 minute before midnight. He gives out candy 1, 2, 3, 4, 5, 6, 7, 8, 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9. And then he changes the first candy. He writes a 0 on the first candy. So it becomes candy number 10. So basically he sort of removes candy number 9, candy number 1. It becomes candy number 10. Now, 1/2 minute before midnight, he gives out candy 11, 12, 13, 14, 15, 16, 17, 18, 19. And he immediately turns candy 2 into candy number 20. He just writes, physically writes. Okay. 1/4 minute before midnight, he gives out candy 21, because we already have candy 20, so we don't need candy 21, 22, all the way up to 29, and he turns candy 3 into candy 30. So after n steps, he has given 9n candy, and the remaining candy is remaining candy are well, you can work out the remaining candy. So the remaining candy are n plus 1, n plus 2, etc. Excluding the round numbers, excluding what are we excluding? Oh, up to 10n minus 1. Right? Oh, yes, up to 10n minus 1. So we have 9n candy remaining. So 9n candy remains. And here, 9n candy remains. Okay. Is that clear? Do you understand the logic between Santa 1 and Santa 2? Okay. Question. Who is the evil Santa? Who's the good Santa and who's the evil Santa? Any thoughts? Is it better now? Okay. So yeah. Any thoughts on who's gonna give out more candy and who's gonna give fewer candy by midnight? Because as time goes by, this is where all conventional logic should go out of the window. Because this is midnight. This is when midnight is when everything stops, where Santa stops giving out candy. So midnight. This is time. So 1 minute before midnight, half a minute before midnight, quarter of a minute before midnight, 1/8 of a minute before midnight. Ding, 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 ding. So who's the evil Santa? No, no ideas? Okay. Imagine Santa 1 gives you candy number 14. 44. I don't know. Candy number 42. Let's make it 42. Let's make it a nice important number. 42. Candy number 42. What happens with candy number 42 with Santa 1? Eventually. Gets taken away. Indeed. What happens to candy number 800? Gets taken away. What happens to candy number 1200? Santa takes it away. And you can pinpoint the exact time when Santa is going to take it away. For any candy, you can pinpoint the exact time somewhere between 23:59 and 12 and 0 hours 0 minutes. You can pinpoint the exact time when the evil Santa, of course, is going to take that candy away. For any given candy will get taken away. Any given candy will get taken from the children. And you can pinpoint the exact time. For any number, you can work out when it's going to be taken away. And with good Santa over here, Santa number 2, of course, any given candy, well, let's take candy number 42. Well, it eventually becomes for candy number 420, but it doesn't get taken away. You just get zeros drawn on that candy. So by midnight, Santa 1 would have taken all candy from the children. Whereas candy 42 becomes candy 420. Candy 420 becomes Candy 4200. Candy 4200 becomes 42,000. Doesn't get taken away. No candy. Candy gets taken away. Away. Only their numbers changed. So this is the good Santa. Good Santa, and this is the evil Santa. Taken away by 1 and adding 10 are both infinite, as in approaching midnight the limit, like asymptotes. Yes. It's effectively the same thing. It's effective writing. So, well, both of them are countable sets. The set of candy given and the set of candy taken are countable. Therefore, there's the same number of candy given and taken. Whereas in Santa 2, there's only candy given. This is something to think about. Like when you're talking about infinite sets, everything you know, all your conventional logic, just throw it out of the window. And welcome to the wonderful world of maths. So yeah, and a somewhat similar approach was the Xenon. Have you heard of Xenon? So Xenon was a Greek philosopher who claimed that that the fastest runner will never catch up with the slowest tortoise. He was kind of a buzzkill in terms of how ancient philosophy goes, but he believed that what is the hare and the tortoise? I think it was, or I think originally it was Achilles and the tortoise. So it's Achilles and the tortoise. I probably misspelled both Achilles and the tortoise. I think it's ACH, Achilles, and the tortoise. So forgive me, please, if you know how to spell them correctly. The tortoise, and that's Xenon. Xenon was the ancient philosopher. So he claimed. So imagine you're running. The Achilles, it was the fastest runner in ancient Greece. And then there's the tortoise. And imagine that the distance between them is 100 meters. Of course, they didn't measure things in meters, but 100, whatever. So by the time, so the tortoise is here and Achilles is here. So by the time Achilles runs the 100 meters, the tortoise would run 10 meters. 10 meters. So by the time he ran the 10 meters to the tortoise, the tortoise will run 1 meter. An extra 1 meter. And then he would run the extra meter, it would run 10 centimeters, etc. So Achilles will never catch up with the tortoise. It's not the same problem. It's, I mean, it just vaguely reminded me when you have a infinite when you have an infinite series effectively. And there are also There are also paradoxes in sets when you have the same thing written in different ways. It gives you different results effectively. I won't remember, but maybe for next time. Okay, so the next question. One publication decided to print a large dictionary. It should include all sequences of Latin letters. And so basically all the letters, all the words, all the possible words made of or English letters. Same as Latin. We use Latin letters. So the first word would be A. The second word would be AA. The next word would be AB, then AC, then AD, etc. Then you would have up to ZZ, right? The last 2-letter word would be ZZ. The next would be AAA, then AAB, then etc. And the last 3-letter word would be ZZZ. And you can kind of see what the logic. So this is the dictionary. However, the publisher decided to distribute it across 26 volumes. So they decided to write 26 books, to split it into 26 books. So the first book would only contain words starting with A. So book one starting with A. So starting A, AA, AB, AC, AD, etc. Book 2 would have only book 2 would have is the book B would have B, BA, BB, BC, etc. all the way up to, well, there's no all the way up to, they're infinite. Okay, etc. And book 3 is C. So it's a very bizarre dictionary. It's only in the you can only see these kinds of dictionaries. These kind of things you can only see in math problems. I'll read your question, Andre. I'll read your question carefully and I'll try to answer. Takes a lot of mental capacity to get into that. So, okay, so you have books. The question, what you need to prove is that the whole dictionary, so the whole 26 books, can take the same number of words as book 1. Or book 2 for that matter. So each book contains the same number of words as the whole dictionary. Okay, so let's have a look. What can we do? What can we do to prove that? Well, we can prove that two sets are identical if we can find a mapping, a one-to-one mapping of one set onto the other. So set 1 in set 2. If we can find a one-to-one mapping, we can prove that they have the same size. Okay. So set 1, let's call it the A set, and set 2 we'll call it the set, the whole. So let's call it, I don't know, U, as in the whole thing. And if we can make a one-to-one mapping, so we can prove that each element from set 1 has exactly one mapping onto set 2, and set 2 has exactly one mapping onto set 1, then we can prove that there's a one-to-one mapping, therefore they are identical. So the first thing we will do is we'll map words containing with just the letters A onto themselves, because both dictionaries obviously contain letters containing A's. So A maps onto A, AA maps onto AA, triple A maps onto triple A. So that's okay. Now, what to do with all the letters that are not just A's? So let's write them out for set 1. So set 1 is we have all the A's, obviously, AA, AAA, etc. Set 2, we still have the A, AA, AAA. Okay. Now now we are interested in the ones that are not just A's. So the first is AB. AB, A, AB, A, B, A, A, B, B, A, no, sorry, AAB, AAC, AAD, etc. And here we have we have B, the simplest one. Then we have C. Oh, I forgot this one. AC, AD, etc. B, C, D, etc. So what I'm going to do is I'm going to imagine that I'm just going to add A to each. I'm going to add A to each word in set 2, except the first, except the words which contain only A's. So add A, add A to each word in set. Add A on the left, otherwise to in set 2. So it becomes A, etc. And so A, B, A, C. And you can see that each element in set 2 has an equivalent in set A. Now, each element in set 2 is has an equivalent, and in set 1. Now, because all the words are different, adding A these words are still different. So all these words are still different, and each word has exactly one copy in set 1. So each word has exactly one copy in set 1. Now we do the reverse. We take set 1 and remove A from the beginning of each word, except for words containing only A's. Step 1. Step 2. Remove A from each word in set 1. Now each of the words on the left has exactly one equivalent on the right. Each word from set 1 has exactly one copy in set 2. Basically, so we have created a function which is a mapping. We have created a mapping which is bijective. That means we have exactly, it's a one-to-one. It's a one-to-one mapping, and therefore the number of words in book A and in the whole dictionary is exactly the same. Both sets have the same number of words. And you can prove that for book B in a exactly the same way. You can prove it for book B, for book C, etc. Does that make sense? Does it make sense what I've just done? Okay, now to your question, Andre. Real on segment 0, 1 and natural numbers. If I get it right, we can prove that the 0.159 C. So if I get it right, can we prove that these? Um, yeah, I see your point. I see your point. It looks like the two you you can have you can have the same real number written in two different ways. Well, the point is that the list contains all possible combinations. So both these representations would be included in the list, if that makes sense. And I don't think I don't see any contradiction here. I'll think about it. I'll think about it. I'll talk to Vlada. She's the math guru in our team. But I don't think I don't think there's a massive contradiction there. But thank you for the question. Thank you for the question. Worth, have you spoken to your tutor about it? Yeah, no. I would ask. I would ask. Maybe they have an insight on that. Okay, so we've done the dictionary. Okay. Now, this problem looks more scary than it is. Prove that if sets x and 1 are countable, then set x times y is also countable. It is known as the Cartesian product, just like the Cartesian coordinates. Defined as the set of all ordered pairs, where the first element of each pair is from set 1, and the second element is from set y, set x and set y. So what does that mean? Well, for example, we have set x contains x1, x2, x3, etc. And set y contains y1, y2, y3, etc. Then set x times y is the set containing pairs x1, y1, x2, y2, x3, y3, etc. X1, y11, x1, y2, x1, y3, and then x2, y1, x2, y2, etc. So all the possible pairs of numbers. We need to prove that if sets x and y are countable, that means that you can enumerate them. You can enumerate the sets, so 1, 2, 3, 4, 5, etc. And that means you can also enumerate these. I sort of already proved that. If you look how I've written them, that is sort of already proof. Because although not quite, because this is infinite. Okay, this is infinite. How do you know? You have infinity of infinities. How do you know they're countable? So what we do, we kind of did this. Sorry, I haven't proved it, but I will. How do you prove it? Well, we've done something very similar last week. And let's label the sets here and sets here. The set here. So this is x, x1, x2, x3, x4, y1, y2, y3, y4, etc. And here we'll have x1, y1, x2, y1, x3, y1, x4, y1, etc. This is going to be x1, y2. So pairs. This is like coordinate pairs. x2, y2, x3, y2, x4, y2, etc. So you need to prove that you can count them. So all you can go start counting 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, etc. So what I've shown you last time, like a web. Or you could go diagonally. You could say start from here, go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. So whichever way you choose, but basically you can go. I prefer the web. I prefer this method. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, etc. So 1, 2. So you can enumerate them. So if the two sets are countable, that means that they can Cartesian product is also countable. Does that make sense? Have I lost anyone here? Do you understand? Do you understand what I did? Okay. Good. Right. Prove that the following sets are countable. The set of all possible finite sequences of 0 and 1. So let's do A. The set of all possible finite sequences of 0. I have two different solutions for this. I'm going to show you both. So the first solution is to write in columns. For example, first, the first column is numbers, is sequences containing just one digit. So it's going to be 1, 0, and 1. That's easy. Then the second column is going to be 0, 0, 0, 1, 1, 0, 1, 1. The next column is going to be 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 0, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. And then you go 4 zeros. 1, 2, 3, 4. And you know the elements. You know that the first contains 2 elements, this contains 4 elements, this contains 8 elements, this contains 16. So you can start enumerating from the Well, you can do it either way. You can start 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, etc. And you can enumerate them like this. You could do a web like I did before, like bam, 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 bam. A bit awkward here. Maybe start from here. 1, 2, 3. Tune, 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 tune. I mean, whatever floats your boat here, but you can count them. If you count them like this, from top to bottom, you can enumerate them. Yeah, so if it's countable if you can enumerate them, and because every column is finite, and that's very important. If you have an infinite number of finite sets, if you have a countable, infinity of finite sets, it's going to be countable. But yeah, so that's it. You have a finite, because the sets are finite, you can count them, and you can tell. You can, if you ask me where is number 144, you can work it out. You can figure out a formula to work out where number 144 is, because you know the system. Because the first has 2, 6, 14, 30. So the next one is going to be 31, 32, etc. This is the first method. Method 1. Method 1, columns. Method 2, I just invented it today, a couple of hours ago. I just like thinking, how can you do it in a different way? Well, look, if you take all the sequences of zeros and ones, so let's write down all the sequences of zeros and ones. So 0, 1, 0, 0, 0, 1, 1, 0, 1, 1, 1, 0, no, 0, 0, 0. What does this remind you of vaguely? No? No one does computer science? So method 2. NCR. Not sure how good this could be NCR, but yeah. It does remind you of binary digits. What's different from binary digits? What makes it different from binary digits? Well, in binary, so in this is binary, and this is 10, base 10. Yeah, the zeros are, because this is 0, this is 1, this is 0, this is 2, this is 3, this is 4, this is 0. So it kind of has the extra zeros, that's what makes it different. So what you do is you can just add Add a 1 to each of them. Add a 1. And now they are binary digits. And if you can see that this is a binary 2, this is a binary 3, this is a binary 4, 5, 6, 7, 8. So it's countable. It's just missing. It's missing the first one, but who cares? Missing the first two, sorry. But it's definitely countable. You can count it starting from, well, you just do minus, you do -2 or -1. So it's going to be 1, 2, 3. So this is in base 10. This is just n. I don't know. The point is they're countable. So it goes, it's just the binary, but it's binary one, but the binary digits, and binaries are certainly countable because they are natural, and that's it. That's the second method. So it's a different way of proving. And now let's talk about the finite sequences of letters in the English alphabet. This is kind of the same question as the dictionaries, and we could have used the same method. So B, sequences of letters. And I'm going to do the same two methods. Hopefully you'll appreciate. Sequences of letters. In the first column, we're going to have one letter words. So method 1 columns. And you have A, B, C, D, E, F, all the way up to Z. The second column will have A, AB, all the way down to ZZ. The third column is going to be A, triple A, all the way down to triple Z. And so how many letters in the first column? How many words in the first column? How many words in the second column? Easy. Yeah, 26. Here we have 26 squared. We have 26 cubed. 26 to the power 4. And how do we know that it's countable? How do we know that this set is countable? Geometric sequence formula. Well, yes, but much simpler than that. Much simpler than that. How do you know that something is countable? Fundamentally. Does everyone know what a countable set is? Yes, you can assign a number to each term. Exactly, to each element, I would say. For each element, you can assign a number. You have just a quick reminder. A set is countable if it's if it's equal in magnitude to the natural number set. This is natural, and this is 1, 2, 3, 4, etc. And if you can assign each letter a number, each word a number, that means it is countable. So you can assign the number 1 to the first word, 1, 2, 3, 4, 5, up to 26, then 27, all the way down to, well, what is that going to be? 26 squared plus 26, 702, and then 703, this is all the way down to plus 26 cubed, up to 18,278. So this word is going to be 18,279, all the way down to something really big, plus 26 to the power of 4. 475,254. So the fact of the matter is that every word in this dictionary, every word has a number. So it is countable. And on a more fundamental note, it is an infinite set of finite. The key word is finite because we know exactly how many elements in each column. It's an infinite number of finite groups. And therefore it is countable. Right? A countably infinite number of finite groups. So it is countable. So yeah. Or you can, if you feel naughty, you can do the web here. You can do bam, 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 bam. Not really recommend. Sorry, not this way. So bam, 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 bam. So theoretically, you can do the web, but it's not very. It doesn't look very nice. The web doesn't nice. You can assign a number to each word. That means it is countable. You could also argue that, well, the alphabet could could represent numbers. The alternative way of thinking. So method 2. Method 2. 2. So imagine A, B, C, Z are digits. Digits in a base 26. In base 26. So letter A is 0, B is 1, C is 2, etc. Z is 26. So A stands for 1, sorry, A0. B stands for B stands for 1. Oh, I've already written that. C is 2, etc. So Z is 26. So after Z, you would have BA. BA is going to be 27. B is equivalent to 1, right? So 1, 1, 0. That's 27. BB is 28. BC is 29, etc. And ZZ is going to be something, right? So this is like base 26 maths. Do you understand what I'm talking about? Honestly. Yes or no? It's fine if no. Okay. Okay, good. So you're familiar with the hexadecimal system? Right. It's very good. Like it's if you're not, please please have a look at the hexadecimal system. It is well, it's a big deal in computing. And by the way, if I haven't mentioned that like 17,000 times already, one of the key skills you need in modern world is programming. So if you're not doing programming at the moment, just do it. Okay. Learn, I don't know, Python is probably the easiest language to learn. So if you go to practice Python, it is python.org, I think it was. Yes. I have done these 40 questions when I decided to learn Python. I did these in 2 weeks, maybe 10 days, and I learned Python, and that's it. That's pretty much all you need to know Python. So if you do these 40 problems, that's all of it, and they all have solutions. So you'll be a very confident Pythoner, not proficient, but experienced Pythoner. At least, yeah. Why is it important? Because like in the modern world, you kind of need to know at least one language of programming, because that really increases your employability. I have a friend who works in the city in London, and I asked, "Who are you?" They said that they were looking for people who want to people to work for, like it's like a huge bank. And I said, "What do you need?" And they said, "Well, we need people who know maths at least at A levels very well, and people who know how to Python." So basically, if you know maths on a like at your level and Python, you are already very employable. So yeah. Anyways, if you imagine ABC digits are in a base 26, and all you need is just the same method. You write them all out. A, B, C, Z, then AA. Once again, we have 0, 0 here, right? The same problem as we had. This is 0, 0. AB, which is 0, 1. We don't write, normally, we don't write 0, 1. So what we do is we write a B. We add a B here. B to each of them. And now we have a sequence of numbers. And this is a sequence of numbers starting with 27. Starting with 27, 28, 29, etc. And certainly a set of natural numbers. So these are base 26 numbers. There's starting from 27, which is a countable set. You can count them. You can attach a natural number, you just 27 less. If that makes sense. So 1, 2, 3, 4, 5. You can you can enumerate them. And the last question is super simple, like really simple. So just for some relaxation. Prove that any two circles on a plane are equinumerous. That means that they have the same number of points. Well, we take a circle, we take another circle, any two circles. If they're the same size, then yes, it's obvious. What to do when they're different size? Put one into the other. Put them in the center. And draw a ray from the middle. Draw multiple rays. And you can see that every point on circle 1, so x1 corresponds to y1, x2 corresponds to y2, x3 corresponds to y3, etc. Okay. And you can see that every point on x1 has exactly one corresponding point on circle. For every single point on circle 1 corresponds to a single point on circle 2. Hence, the two circles are equinumerous. And that was the argument. That was pretty much the argument made by Democritus in 600 BC, circa 600 BC. So his argument was, well, one of his arguments was that if you have before him, it was thought that matter was continuous, right? Matter could be infinitely split. So for example, if you take some water, water can be infinitely split. So Democritus 600 BC. It would be embarrassing if I'm wrong. Democritus. 460 BC. Okay. I'm off by a couple of 100 years. So 460 to 370 BC. So he argued that matter is not continuous. Matter is not continuous. That means it cannot be split infinitely. Because if it was, a 1 meter ruler would have the same amount of matter as a 10 centimeter ruler. He didn't say a 10 centimeter ruler, of course, but that was his point. Because if you draw a 10 centimeter ruler and a 1 meter ruler, you can find the equivalents. Every single point on a 10 centimeter ruler has an equivalent on the 1 meter ruler. So he said it must be made of atoms. He said matter must be made of atoms, because clearly the longer ruler has the same number of atoms. So the longer ruler has more atoms than the short one, and that way you cannot make a one-to-one. So we're coming back from math to real life. In real life, you can a meter ruler has more atoms than the 10 centimeter ruler. Now here, the circle is not a physical circle; it's a mathematical circle, and that's why they have the same number of points. But a real circle is made of atoms, and there's clearly more atoms in those, and this is why it's so difficult to understand. It goes, but it clearly isn't, right? Clearly isn't less dense, because you can measure the density of the longer ruler, and it's the same. They knew about density, right? If you remember Archimedes and his famous Eureka. There's a statue of Archimedes in Manchester. If you're in Manchester, if you walk from the Piccadilly station to the university, along the train line, you'll see the statue of Archimedes in a bath. It's called Eureka, I think. I look it up. It's good. Mathematically less dense. It doesn't mean anything mathematically, because we're talking about infinity points on the first circle and infinity points on the second circle, and that was his point. You cannot have infinity. A ruler cannot be made of infinity points. You cannot infinitely split matter. There will be a point where you're splitting atoms, that you've reached an atom, and it's atomos means indivisible, and he realized the existence of atoms. Well, that was what, 2,500 years ago. But you can infinitely split. Yes, because a line is a mathematical concept. You can infinitely split a line, but not a ruler, not a piece of paper. Okay, I'll finish here for today. I really enjoyed this session. I hope you too. And I hope you learned something new today, and always glad to be of help. see you. Is it due this week? I kind of lost. Okay, due this week. Okay. All right. Well, enjoy the weekend then. See you.